In this first section, we're going to talk about what we might call the network paradigm. All models and theories are like windows onto the world. None of them are perfect. They enable us to see some things, but also inhibit us from seeing others. And more importantly, they all rest upon some set of assumptions. This set of methods and assumptions that support a particular scientific domain is called a paradigm. So before we can start to get into the technical side of network theory, we want to make you aware of some of the key features to the network paradigm. These features will constitute major themes that we will be rediscovering and trying to highlight as we go through the course. Firstly, networks are all about connectivity. Within systems whose components are relatively isolated, we can focus our interest on the individual components within the system. By analyzing their properties, we can gain an understanding of how the whole system works. For example, say I've put together a financial portfolio of different assets. Well, if the risk on these different assets is not correlated in any way, that is to say that they are all from very different sectors of the economy, well then I can calculate the overall risk of my portfolio by simply analyzing the properties of each asset and then summing them up to formulate a total value for the overall portfolio. But what if many of the assets in my portfolio are correlated? If I've acquired many investments within both, say, the food processing industry and agriculture, well, the risk on both is correlated, or assets in both logistics and retail, which are again interconnected. Because of these correlations, the value of the assets will move together. Thus, the real risk-return ratio on my portfolio is no longer defined by that of each asset in isolation, but now by these correlations. That is to say, what is connected to what, and in what way are they connected, comes to now define the whole system. The point to be taken away here is that we often spend a lot of time analyzing individual components, and then assume the whole system is simply an additive function of these parts. But when we turn up the connectivity within a system, it is increasingly the relations between the components that comes to define the overall system. And this is where network theory really finds its relevance, as it is all about connectivity. To go back to our financial example, hedge fund managers and other financial institutions don't go out of business because they fail to analyze the characteristics of their assets in isolation. They go bankrupt and we get financial crises because we don't see the networks of connections between these assets. To see the world through the network paradigm, we need to see not just things, but the connections between them. And this leads us to our second point, that is, that this world of connectivity has a very different kind of space to the one we are used to. We've spent our lives walking around in a three-dimensional space, what we call a Euclidean geometry, that is deeply intuitive to us. But we need to forget about this, because this is the geometry of things or objects and not of connectivity. The geometry of networks is what we call their network topology, and this topology stretches and bends our three-dimensional space around it. So let me quickly illustrate this to make it more clear. Say I live in Istanbul, Turkey. If we pull out a map, we will see that Budapest, the capital of Hungary, is much closer than London. But because London is a major hub in the global air transportation system, whilst Budapest is only a minor one, it is much easier to make a connection to London instead of Budapest. So if we put something in this network at Istanbul, because of the network's topology, London is essentially closer to it. Hopefully, this will give some insight into how networks operate in a different type of geometry than the one that we're normally used to, and thus they cut across our traditional domains, not just in space as in this example, but in all areas, making the study of networks a truly interdisciplinary one. Thirdly, networks represent a very organic type of structure that often emerges from the bottom up, but also has some environmental constraints imposed upon it. Examples of this might be the trading routes that have emerged at different periods in history. During the Middle Ages, traders from Asia would exchange goods with merchants in India and the Middle East, who would in turn bring goods to Europe and vice versa, thus emerging an almost global network of trade routes. Out of the local interactions between the merchants, no one planned this whole system, it simply emerged. The same can be seen in an ant colony, where individual ants leave a trail of pheromones to food sources. Here again, a network emerges out of the different ant trails. But none of these connections and the networks that emerge out of them are for free. They cost something to maintain, and thus many of these networks are a product of the interaction between the local elements that are creating the connections and the environment that is placing some resource constraint on its development. We will come back to illustrate this point more fully later on in the course. Lastly, complexity and nonlinearity are inherent features to networks. As the number of elements in our network may grow in a linear fashion, as in 1, 2, 3, and so on, but the number of connections between them may grow in an exponential fashion. So if we take just a small group of people, say 10 or 20, there can be literally billions of different types of networks between them. Nonlinearity will be a reoccurring theme, and we can only approach this type of exponential complexity with the use of computers. When we combine this new way of describing the world that network theory provides us with powerful tools of computation and a flood of new data sources that we now have available to us, we get a mini revolution, a new approach called network science that is starting to have a major impact on many of the traditional areas of science. Networks give us a very intuitive way of visually representing complexity, and this can give us a quick and intuitive overview to a complex system. By just looking at it, we can get a quick sense of how connected it is, what are the key nodes, and other critical information to understand the whole system. I hope at this stage you've got an idea for what we mean by the network paradigm. It's about connectivity, the fact that this connectivity creates its own type of space and geometry, one that is often defined by how the elements in the network created the connections and the constraints its environment imposed upon it, with this world of networks often being non-linear and only really approachable through the use of computation.